right, 11:15. Let's get started. We are going to be kind of jumping around all over the place today, but again, all of this is directly relevant to the robot project. First, some debugging tips. So this slide should be up on the projectors and TVs in the lab. So you've kind of done individual homework assignments and labs where you're doing one thing throughout the semester, and now you're piecing them all together. So it's not quite at the ASML level, where I believe Olaf mentioned they have some huge machine with 40,000 cables in it, right? But you're building a robot with a few sensors, a few motors, and maybe on the order of a dozen or a couple dozen wires, right? So if you put your robot down to do the first milestone and it turns left and it should have turned right, or you go to do the next milestone and it drives over the black border, right? That is the symptom or the result, but there are basically infinite things that could cause that. Okay, so as we've talked about throughout the semester, we kind of have that debugging mantra up on the whiteboard in the lab. You have to isolate the issue by dividing it into subsystems and figuring out where the problem is. Okay, so I want you to go through this process before you just raise your hand and tell the TA, my robot doesn't work. Okay, if that's all you tell the TA, they really cannot help you. Okay, so this is not an exhaustive list. This is kind of for the standard robot build, right? The main parts most of you are going to use. Obviously, everybody's going to have different designs, and this is going to diverge. But at least some pointers for kind of the main systems when you go to, you think you have everything coded and wired correctly, and you put your robot down, and it just like drives off and does whatever the hell it wants instead of what you want it to do, right? H bridges, okay? You're now building a robot with 2 H bridges to control the 2 motors. There are a couple different ways you can just verify that your H bridge is wired correctly, right? You can forget the Arduino completely, don't connect to the Arduino I/O pins, you don't even need to be running any code, and just connect the H bridge's input pins directly to 5 volts and ground, right? If you connect one to 5 volts and the other one to ground, if everything's wired properly, the motor should spin one way, and then if you swap them, so the other one goes to 5 volts and the original one goes to ground, it should make the motor spin the other way. Okay, that lets you verify that your H bridge is wired correctly, independent of what your code is doing. Okay? Independent of how your H bridge is wired, you can also check what your code and your pins are doing using either a multimeter or an oscilloscope. Okay, so if you're just using the port register to set a pin high or low, you just hook up a multimeter and go, okay, yeah, this pin is actually toggling high or low, like I think it is. Or if you're using PWM, like we started talking about on Wednesday and we'll be talking about today, you hook up an oscilloscope and look at the pin and say, am I actually getting a PWM signal out like I think I am according to my code? It is possible to damage individual I/O pins without damaging the rest of the Arduino. Okay, so if either your group or some other student in years past who you can blame has shorted an individual pin, pin 6 might be broken if everything else is working fine. Okay, so if you do the first bullet here and everything is wired correctly, but then it doesn't work when you hook it up and try to run the code, make sure you look at the actual output pin. If that pin appears damaged, just ask the TAs to swap out and give you a new Arduino. Okay? Or short term, immediately, you can always just move to a different pin. Longer term, if you need that pin for something, the TAs can give you a new one. Okay, so that's for the H bridges. Sensors. At minimum, you're probably going to at least have the color sensor. You are probably going to have these 2 QTI or line sensors, which we're going to talk about next week. That is not mandatory, though. If you want to build an effectively blind robot with no sensors, technically you can. But assuming a lot of you are going to be using these, again, independent of how any code is running, you can look at the sensor output on either an oscilloscope or a multimeter. Okay, if your color sensor is wired right, it should give you that square wave output that you saw on the oscilloscope in lab 4, right? If you're not even getting that output from the sensor, then it doesn't matter if your code is right, the sensor's not working properly. Okay, so then that's kind of verifying individual hardware components. You are going to be connecting these things using code, right? You are making the motors react to the sensors. So, in basic example, if the robot is supposed to drive forward and stop when it sees a line, but it doesn't, all you observe initially is that the robot just drives off the edge, then if your robot's driving forward, so at least you know your H bridges are probably working, but did it drive off the edge because your sensors are not wired right, or maybe your sensors are too far from they're wired right, but they're too far from the ground, so the amount of reflected light isn't sufficient, or is there something wrong with your code? You don't know until you investigate all of these things. So with the code, I put this in bold, use serial print for debugging. Okay, you cannot, when running code on the Arduino, you cannot see what the code is doing unless your robot is still tethered to the computer and you are using serial print. So you can print values of registers or variables to make sure they make sense, and that the period for the color sensor is a good example, printing that out and make sure you're getting the expected period reading. You can also place serial prints in strategic locations to kind of check your code's logic. So very simple example with a button, right? If you have an if-else statement, just using polling to check if a button is pressed, put in a serial print that says button pressed or button not pressed, which lets you tell, again, if you just have it wired on your Arduino and you're pressing the button and some hardware is supposed to be moving as a reaction, right? But it's not, you can't tell, okay, maybe that's because my output, there's something wrong with my output hardware, or it's not even detecting the button press. That's what the serial print is for. Same thing with interrupts, right? You can put serial prints in interrupts, say interrupt triggered. If you have a loop incrementing, you want to keep track of a variable, whatever. Again, this is open-ended and going to branch out, but the point is, I am going to tell the TAs not to help you until you've done this. Okay, if you just call them over and say something's wrong with our code, and they go, okay, have you used serial print to debug, and there's not a single serial print in your code, the TAs are instructed to walk away and come back once you have done that. Okay, you can't just throw them a giant screen of code and be like, find our problem and fix it for us. Okay? Questions on kind of this philosophy or process? Again, with the caveat that this is not an exhaustive list of everything that could go wrong or every step you could take to debug it, but this is kind of the, I think, the big three as you're getting started with the robot. Nothing? Okay. How was heat transfer? Are you all in shock? Thumbs up, thumbs down, yay, recovered, ready to go build a robot. I see the lab is very full this afternoon, so I'm kind of assuming now that everybody has heat transfer out of the way, we can focus a little more attention to the robot. Okay, like I said, we are jumping around today. We're going to switch from PowerPoint to Tinkercad and where we left off last time. Okay, so at the end of Wednesday, we should have gotten this far. So I'll give everybody a minute to pull Tinkercad out. Where again, we don't have a motor wired here, we're just using an LED. And actually, I lied, while you guys are doing that, I'm going to switch to the document cam, but you don't need to write anything here. I just wanted to show the document camera. 3 types of motors on camera here, in case you have not seen these in your kits yet. So there's the larger black motors, right, that were originally 3-wire servo motors, but are modified to only have 2 wires. And so these are the ones that are going to drive the wheels in your robot. You must use these to drive the wheels according to the rules. You cannot purchase larger motors to drive the wheels. Okay? These are controlled using an H-bridge like you did in Lab 3. The wheel just kind of snaps on to the output shaft here, and then I believe there's a little screw that connects it. You also have smaller servo motors. Now notice how these have 3 wires. And so I mentioned last time, these have a power wire, a ground wire, and a control wire that we are going to send a control signal to. We'll talk about that later today if we get there. They also have just this little plastic output shaft here, and they come with what's called servo horns. So there's this little kit with these different shaped little thingies that screw on there and have mounting holes. There are screws in the lab that you can use to mount stuff to them. So if you want to 3D print some adapter or bolt a little acrylic rod onto there or something, you can. There are 2 different kinds of these. Positional, so these have a range of about 180 degrees. The control signal you send to them is going to control the angle. Okay? There is internal feedback that will do its best to drive it to that angle, even if you apply a load to the arm. These are cheap little servos with plastic gears, so you do not want to load them too much or you're going to strip the gears. Okay? It's not a good idea to just grab the shaft and like back drive one just to see what will happen. But for purposes of getting you through this project or picking up cues or something, that's probably sufficient. That is the positional ones. If you look closely, some of them, I can zoom in there, have a little 360 on them, so otherwise they look exactly the same, but that 360 means it's a continuous rotation servo. So rather than having a limited range of 180 degrees, these can spin continuously in either direction, but you cannot directly control their angle. You can only control the speed and direction in which they are rotating, but you can't say rotate to 90 degrees. Okay, so depending on the type of mechanism or appendage or whatever you are doing with your robot, one of these might be more appropriate than the other. And again, we are going to talk hopefully later today about what the control protocol is to the third wire there and how that's different from controlling the speed of one of these guys. Okay? Again, you didn't really need to write anything down there, I just wanted you to see them. We are going to switch back to Tinkercad. Okay. Recap of what we did last time. We kind of wrote down on paper what we needed to do with the TCC-R2A and TCC-R2B timer control registers to set this timer up for PWM mode, so we can either dim an LED, just as an example, so we're not worried about the motor wiring, or so we can control the speed of a motor, which you need to do either if you really care about your robot driving straight, or you want to be able to kind of do gradual turning maneuvers instead of just turning in place. Okay, so we should have had all these values jotted down last time, but I am going to kind of write some comments here. So setup code that only runs once. You still need to set the pin you're using as an output. And then we're going to do a few things for the timer control registers. Why is it not typing? This would be as soon as I can figure out why Tinkercad won't let me type. Hold on. This would be a very bad time for my keyboard. Okay, there we go. Bad time for my keyboard to freeze. Okay. Set up timer control registers for PWM. Okay, so we're going to use the WGM bits for phase correct PWM modes. The WGM bits were 001, but remember those were split across. And I'm not going to bother toggling back and forth to the data sheet a dozen times like we did last time, because we kind of went through all this last time. This way you just have it in the comments for the code. Okay, the CS or clock select bits for prescaler to 1, that was also 001, but test different prescaler values for your motor. So again, if that frequency of that PWM signal is too high, the motor acts like a low pass filter, it won't actually move. If the prescaler is too big, then your motor's speed might actually oscillate. You'll see it turn on, see it turn off, as opposed to going at a continuous speed. So you kind of, I think when I did this last, I used a prescaler value of 256 and that worked best, but again, all these motors are a little different. The loads on them are going to be a little different. So that is just the initial value to turn it on, but then you're going to want to change the prescaler to see what works best for your motor. And then the COM bits to, which one did we do? Clear on up counting, and that was COM to B1, COM to B0 equals 1, 0. So that's just getting all the values from the datasheet table into here. So if people don't remember that or have questions from last time, I can pull up the datasheet again. So is everybody hopefully remembering this from Wednesday? Okay, so think of these just like all the little control switches or settings we need to turn on and able to enable PWM mode. Once you've gotten that headache out of the way, you only need to do it once at the beginning, and then there's just a single register we're going to need to change later to change the speed or the duty cycle of the PWM signal. Okay? And again, I kind of jotted those comments down there. If this makes it, you have a better way of writing this down such that it makes sense to you, you can write whatever you want for the comments. Okay? So writing down what we had last time, again, we're not going back to the data sheet. TCC-R2A, 0B, 001, 0, 0, 0, 0, 1. Okay, so 2 zeros and a 1, and 4 zeros and a 1. TCC-R2B, 0B, 7 zeros and then a 1. 1, 2, 3, 4, 5, 6, 7, 1. Okay, and all of that is doing what we've kind of laid out in the comments here. Okay. Questions on that setup? Okay. Once you have that set up, all you then need to do for the rest of your program is change the value of the OCR2B register to change motor speed. Okay, where 0 is fully off, 255 is fully on. So 0 is 0% duty cycle, 255 is 100% duty cycle, and then anything in between, again, it's this value will map linearly with duty cycle, but not necessarily linearly with motor speed. Again, especially at very low speeds, it might not overcome the internal friction. So if you try to set it to 5 or 10% duty cycle, it just might not spin at all. Okay? So wherever you want to change the motor speed, for example, if all you want to do to test that you've set everything up right is just have the motor go full speed, all you would need to do is just type that. Right, so now what you do with this is now going to depend on the logic of your code, what your if statements and interrupts or for example, the drive forward and turn left functions we did last time. You would put this wherever you need to change the motor speed. Okay? If you want to turn the motor on full speed, you do that. If you want to turn it on roughly half speed, you do that. Okay, so some good example of code you can write just to test that this is working is to just ramp the speed up and down using loops. And so for example, you could do while OCR2B is less than 255, sorry, losing my mouse. And actually one more thing I'm going to do up here, I'm going to enable serial printing, and then in my while loop, I could, excuse me, print out the value of OCR2B, and then say increment it, OCR2B++, just increment it by 1, and add a short, I'm going to scroll down because that's kind of low there. So add a short delay, like a 10 millisecond delay. So all that's going to do is OCR2B will start at 0, it'll print out the 0, it'll increase it by 1, and then add a short delay, and keep going through this loop until it gets up to 255. Right? Or sorry, well, that loop will execute while OCR2B is less than 255, so the last time it enters this loop, OCR2B is 254, it sets it to 255, which is the max value, and then it exits the loop. Okay? If I want to then ramp back down, I just copy and paste that loop, but change the condition to do it while this is greater than 0. And this time I'm going to subtract or decrease OCR2B by 1. Okay, so this code is not useful for your robot, but this is useful to demonstrate that you have set up PWM correctly and see how your motor responds. Okay, you run that, your motor should be stopped, it should ramp up to full speed and then ramp back down continuously and just keep looping through that. Okay, so yeah, that is just a demonstration. So if you go copy and paste this code in a week, if you ran this on your robot for both wheels, then all it's going to do is make your robot drive forward and backward, right? Actually, sorry, this would make your robot drive forward full speed and then slow down to stop. This would not make your robot drive backward because it is only controlling one of the H-bridge pins. Okay, so to switch. Remember, to switch direction on the robot, you have 2 pins. You need to set one high and low. So maybe I'll switch to the document cam actually to explain that real quick. So I'm not sure if that makes sense. So I'll come back to this in a second, but I want to switch to the document cam. So without bothering, this is not the correct circuit diagram for the H-bridge, so don't take this too literally. I'm not going to bother with all the pins, but you have your H-bridge, which has 2 output pins connected to the motor, right? And before we saw if you set, and then there's the 2 input pins to the H-bridge, so if you set one high and one low, the motor will spin one way. If you set reverse that, the motor will spin the other way. Same idea here. If we send a PWM signal to one, and just set the other one low, and say the motor will spin one way. And if I'm going to reverse that, if I want to spin partial speed in the other direction, then I need to send a PWM signal to the other pin. Okay, so if I say only care about controlling my speed when I'm driving forward and not about when I'm driving backward, then you don't necessarily need the PWM signal on that other pin. This one can just be a digital, purely high or low. If you only want to go backwards full speed, but you want to control your speed when you're going forward, then you only need one PWM signal. If you want to control speed in both directions, you need two PWM signals. Does that make sense? Okay, and that means if we go back to the code, everything I've done here would also apply to the OCR2A register, which is on a different, I think, pin 11. Again, I don't have the tab for the data sheet pulled up. So we would also use OCR2A, check pinout diagram for second. Otherwise, you would also need to set the timer control registers for that, so would need to set COM bits. Okay, so right now, again, there's two other bits in TCCR2A that we left to 0 because we weren't using output compare A. So if you wanted to use that and have two PWM signals, you would also need to set this up. Also remember that we have done all of this for timer 2. Pretty much everything we've done here also applies to timer 0, but you need to go look up the TCCR0A and TCCR0B registers in the data sheet. So this all depends on how many PWM signals you want and which pin you're using. So I can't just give you a single example program that will work for your robot, because at this point everybody's robots are going to be different. With me, lost. Don't care because you're just going to make your robot drive full speed the whole time. You guys got to give me something. Thumbs up. Great. Question.
Gotta go fast.
Gotta go fast. Exactly. Okay. Sure.
How would you go slow? It's a competition.
Well, usually the other person's strategy.
Okay. And again, everything we've talked about so far applies to the black motors. Okay, these 2-wire black motors. So I don't know if you want to write that in the comments somewhere so you don't get this mixed up later. Okay, this applies to the black motors that have 2 wires for controlling your wheels. All right, everyone good on the Tinkercad? I realize you kind of scrolled up there, like need a minute to copy anything, and you're typing. Okay, again, I will be posting a link to a better commented version of this later today. So, but again, I think it's a good idea to type it out yourself and have your own comments too, instead of just copying mine, because my style might be different. Okay. We are going to switch back to the document camera. And now we are going to switch gears to talking about, so again, that was for 2-wire DC motor there. Hobby Servo. Protocol, which for this class is the little blue ones. It is going to be a PWM signal, but it kind of looks different. So Hobby Servo Control Protocol is kind of like an industry standard for these little tiny hobby servos that are commonly used with Arduinos. Larger industrial servos can have a different control protocol. It uses a PWM signal, but it is a 50 Hertz signal with a 20 millisecond period, and the positive pulse width ranges between about 1 to 2 milliseconds, which you can tell is only about 5 to 10% duty cycle. Okay, so this does not go from 0 to to 100% duty cycle. Unlike what we drew last time, okay, where we started at 0 and then we had, I'm not going to draw all of them this time, but we had 25%, 25% up to 100% where it's high all the time, which isn't that a song lyric or something, but anyway. Okay, not from 0 to 100%. Okay, so don't get these mixed up when you are controlling the hobby servos. The duty cycle is only going to go between about 5 to 10%. Okay, this is just an industry standard that somebody made up at some point, and there is actually, if we were to crack open the case and look inside one of these, there is a tiny little microcontroller, not as big as the one on the Arduino, that is converting this pulse for the positional servos to an angular output. Okay, so there's also a little potentiometer for the positional ones in there, measuring the angle. There's a feedback circuit that will control the angle. Okay, so this is corresponding for that pulse. Say, for example, roughly the 1 millisecond pulse is going to be 0 degrees. The 1.5 millisecond pulse is going to be 90 degrees. And 2 millisecond pulse is going to be 180 degrees. Okay, so the period or frequency of the signal, the distance between the rising edge of these positive pulses is not changing, but the width of the positive pulse is what's controlling the angle of the servo. Okay? Let me see if I can cram this in on this page or if I'm going to need a new one. To generate that, we are still going to use a timer. I'm going to start on a new piece of paper. This is going to get too crowded. Still going to use the timer PWM mode, but we're going to use a slightly different mode. Okay, so we still have our 8-bit timer that can count up to 255, but rather than counting all the way up to 255, we are now going to pick a different top value. Timer is going to do just what it did in the other PWM mode. It's going to count up and down, count back down once it hits that top value. And we are also going to select an output compare value. And what this is going to do, changing that top and output compare value is going to allow us to control both the frequency and the duty cycle of the output PWM signal. Okay, so when we did this before, and it was always counting up to 255, and we just moved the output compare, and I drew this last time I think, that let us change the duty cycle, but we couldn't control the frequency. We couldn't kind of control the width of these triangles. Now, by controlling top, we also can change the width of the triangles and control the frequency, because we need to get it to exactly 50 hertz to work with the servo control protocol. I haven't tried to see what happens if you send it a 60 hertz or a 30 hertz or some other signal, but it's kind of going to, in general, make the servo go haywire and not go to the angle that you want it to. Okay, so again, drawing out the resulting PWM signal from that. We still are going to be toggling a pin where those lines intersect. Okay, so if the pin starts out high, goes low when those lines intersect, and so on, then the resulting PWM signal is going to look like this, where again, now if I move the output compare value up, this is assuming I'm clearing on up counting. If I move the output compare value up, then the low part of that pulse is going to shrink. So higher output compare value means higher duty cycle. Okay? We can calculate the period of that pulse in nanoseconds using the equation 2 times 62.5, which is again the one clock tick in nanoseconds, times that top value times the prescaler. Okay. To wake everybody up a bit, we're going to do this one as a poll everywhere, which I forgot to pull up before lecture, so bear with me. Over here. But maybe for those of you with historical poll everywhere login trouble, Now would be a good time to start pulling that up. All right, I want you to find the top and prescaler values that will give a period of exactly 20 milliseconds. Okay, start working on this before you do the poll everywhere. Find top and prescaler values for period of exactly 20 milliseconds. So top has to be between 0 and 255, and the prescaler options you need to look up what those can be for timer 2 in the data sheet, roughly around page 203, and then scroll down. Okay? So top can be anything between 0 and 255. It cannot be a decimal. It can only be an integer value. There are only certain prescaler values available, and you need to go look at that clock select bit table in the data sheet to find out what they can be. Doing that, and then once I don't have this set up as multiple choice. It's a free answer, so no LeBrons or pumpkin ice cream or anything else. Just enter both numbers as comma separated values. So this should be clear in the question, but for example, if you found that top was 10 and the prescaler was 64, which is not the answer, you would write 10 comma space 64. Okay, this is going to help me gauge if this made any sense to you guys at all. Okay, remember our goal is to kind of use this method to generate this signal. Okay, and right now we're not actually worried about the duty cycle yet. We're just looking at how do we get a 50 hertz signal out of this timer. Okay. And sorry, I said exactly 20 milliseconds, but let's say that as close as possible. As close as possible to 20 milliseconds.
Is that nano or Professor, is that nanoseconds or?
Oh, sorry, 20 milliseconds.
Oh, sorry.
Sorry. 20 milliseconds. Because the hobby servo control protocol, as far as electrical frequencies go, 50 hertz is pretty slow. Right? So that is a 20, apologies for terrible handwriting, millisecond period. Okay, I've got 33 responses so far, so I assume people are still working on this. We'll give it a few minutes. While you were working on that, I will mention that there is, as usual, an Arduino library that makes life much easier that you are not allowed to use for this class. So there is an Arduino Servo library. Which will just let you send an angle, so you can use a command called servo.write angle, where that is a number between 0 and 180, but the documentation for that library doesn't tell you anything about timer. It doesn't actually tell you how this symbol is being generated. And as a reminder, if you hate doing this, again, you're paying to go to Cornell. Everybody else in the world can just find that on the internet for free. So now you actually understand how that works, ideally. That is kind of the underlying motivation for why we're making you do it the hard way. Okay, I didn't have the tab pulled up, but pull up the data sheet, go to the page for timer 2, scroll down and look at the prescaler values, and then technically you have one equation and 2 unknowns, but since there are a very small finite set of choices for the prescaler values, it shouldn't be that hard to calculate the top value. And keeping track of units, this equation, because of the 62.5 there, will give you the period in nanoseconds, but we want a period of 20 milliseconds. Okay? Informal survey of laptop screens shows that most people are not actually working on this problem, so let's just speed up the poll. And I have 78 replies. I'm going to give it 20 seconds. Actually, I'm going to pull up the data sheet while I'm waiting for that, so you get a little more time. My tab's open for this today.
Professor?
Yes.
The data sheet is below in the course reference materials, right?
Correct.
Okay, and it's called Arduino data type?
ATmega 328p datasheet.pdf.
So that one.
Yes, that one. Hopefully this is not the first time you've opened it this semester.
It's not, but I thought we were working on a new thing.
Okay.
That makes more
All right.
sense.
I'm going to close this so we can keep going with the last 15 minutes. 5, 4, 3, 2, 1. Deactivate. Let me check the responses.
Come on.
Okay. So, oh, I forgot I had this as a word cloud, so hold on.
Professor, can you
Yes.
reopen it for like 5 seconds?
Okay, fine. Reopening. 5, 4, 3, 2, 1. Deactivate. Okay. Then it looks like, switch to laptop. The word cloud format here does show 1024 and 556, which are the two, sorry, 1024 and 156, which are the two correct values. So if we switch back to the document cam, okay, so if you multiply out 2 times 62.5 nanoseconds times a top value of 156 times a prescaler of 1024, that gives you a period of, I think, 19,968,000 nanoseconds, which is pretty darn close to 20 milliseconds, okay? So if you did this calculation the other way and started out with 20 milliseconds, I think you get 156.25 or something, but since you can't enter a decimal value for the register, then you have to truncate that and get 156. Did I see a hand in the back?
That's my question. Top has to be an integer.
Yes, top does, since it's stored in an 8-bit register, it's an integer value, it's not a float, it cannot be a decimal. Yes.
I did 250 and 60.
Sorry, you did so if you 250 and 64 for the,
Actually, never mind. That's
okay. I was saying, so there depending on the period you want, there might be, well, again, this is one equation and 2 unknowns, so I haven't checked if there are other possible solutions, but I think that I think when I did it, the next lowest prescaler value was 256, and then it was impossible to find a top value in the allowable range. But I don't have the math for that jotted down. Okay. All right. Let me pull up the data sheet. So, we know how to get laggy, a period of exactly, or very close to 20 milliseconds, but how do we control that top value? Okay, remember in the previous PWM mode we picked that top value was just always 255. We are going to control it using a slightly different PWM mode. So if we look at this table, we see there are two PWM phase correct modes. The one we wrote the code for before, this table has a column for top value in it. The top value is 0xFF. Remember, we really briefly talked about hexadecimal numbers and just how this is a more compact way to represent a number than binary. So the top value there is 255. It's always going to count up to 255. The top value for this one is OCRA. So we can pick the top value for this one using a corresponding register. Okay, that is what is going to allow us to control both the frequency and the duty cycle. Okay, so switching back to, let me think. We have 9 minutes left. I'm going to switch back to Tinkercad. Make sure you clearly label this circuit, again, whatever you want to call it. This is 0 to 100% duty cycle. Actually, I'll put this in the comment here. So this is for 0 to 100% duty cycle for controlling DC motor speed. Uses default top value of 255, okay? So in other words, this is for controlling speed of the black motor. So you don't get your two different PWM programs mixed up in the future. Make a copy of this one, and we're just going to do some quick modifications to change it to work for the servo instead. Okay, so I'm going to pull that off camera real quick. Okay, so rename this one Hobby Servo Control Protocol or something. Real quickly, we're going to delete the LED because Tinkercad, it's not as complicated as wiring an H-bridge. The nice thing about these servos is all of the control circuitry is internal, so you can actually wire them directly to your Arduino. There is no external H-bridge required. Okay, these things have 3 pins, so they're orange is going to be the signal, and Tinkercad will tell you this if you mouse over. Red is power, and brown is ground. So when you connect these to your breadboard, it's going to have common ground with the rest of the circuit. Power, these run on 5 volts, not 6 volts. So that is, I don't think the 6 volts is high enough to damage them, but maybe write a note of that. Power with 5 volt. Actually, I need to double check the data sheet to see if these can handle up to 6 volts and check with Dave Martino. So check data sheet for voltage rating. Generally, good rule of thumb or good practice is not to power motors directly from your Arduino's 5 volt rail because the Arduino can't provide that much current, but usually just for 1 or 2 of these little servos you can get away with it. The risk is that you don't want to burn them out by applying too much voltage. So again, I do not remember off the top of my head the voltage that they are rated for. Double check that. I need to see if the data sheets are on Canvas, or if not, get them from Dave. Double check that before powering them. And then our control pin, I'm violating my own rules with being messy about wiring here. We're going to keep as pin 3. Okay? The only change we're going to make to the code, where again, this still will not run properly in Tinkercad, is that this is going to be our Hobby Servo Control Protocol. So 50 hertz signal with 20 millisecond period and roughly 1 to 2 millisecond positive pulses to control servo angle. Pretty much all of the setup is the same, okay, except we're going to, we only have 5 minutes left, so rather than having you guys look all of this up in the data sheet, I am just going to type it in so you have the code. we're going to set it to mode 5 instead of mode 1, okay, which is that, oh geez, freak out on me now, okay. Again, mode 5 here is the space correct PWM mode where we can control the OCRA top value, okay, so now the WGM bits are 101 instead of 001. So just change it here, WGM equals 101. We are going to set the prescaler to 1024, okay, which makes the CS bits, if we go over to the table, 101. Okay, so CS bits to 101. We're going to get rid of this part about testing different prescaler values for the motor. That no longer applies. COM bits are still clear on upcounting, so that is still 01. Okay, so our TCCR2A and TCCR2B registers should now look like this. 001, 000, oops, get that right, 01. And so I think the TCCR2A register didn't actually change. TCCR2B becomes 0, 0, 0, 0, 4 zeros and then 4 ones. Okay, so again, make sure you get the comments right. We changed a few things. We set it to this different PWM mode that lets us control the top value. We set the prescaler to 1024, and then we didn't change the clear on upcounting thing. Okay. We now need to set top value using corresponding OCRA register, which in this case is OCR2A because we're on timer 2. So that's going to be the value we calculated. OCR2A equals 156. Don't change that one. Okay, that is just setting the top value. That is setting the frequency of the signal, which is going to stay the same for the whole program. Okay? We are now going to, again, if you want to do a demo where you just oscillate the servo back and forth, ramp up and down that OCR2B register. The difference is this time we are not going from 0 to 100%. Remember, we're only going from about 5 to 10% duty cycle change. Okay, so we can set that to some initial value. So not change motor speed, change servo angle, where very roughly, if you do the math, I think I failed to jot these. Hold on, I'm sorry, give me 1 second. I had the values somewhere and then this was up. We are going to have, so I have values of 3 and 21 written down, which is a little outside of the range. 21 winds up giving you, I think, a 2.6 millisecond pulse. So again, 1 to 2 milliseconds is kind of a nominal thing. Some of them you can actually push outside that and it'll go a little farther. It's going to depend on the exact servo. I believe this should work for these. So, for example, if we want the servo to start at 0 degrees, go over to 180, and then come back, we're going to start OCR2B at 3. And then we're going to go up to 20, so we're only going to go back and forth between 3 and 21 instead of from 0 to 255. Okay, so, well, this is less than 21. So we do that, and then, well, it's greater than 3. And sorry, that was kind of fast, but we only have 1 minute left. So again, remember what I showed in the document cam, we're not going between 0 and 100%. We're just kind of going between that 5 and 10% duty cycle. So what you'll notice there is that with an 8-bit timer, that doesn't give you very good resolution. Okay, there's maybe almost 20 angular positions. So for a 180-degree range, that gives you roughly 10-degree increments in which you can control the servo. Okay. If you want finer resolution, you could do this with the 16-bit timer 1, but you are probably using that for your color sensor. So if all you need to do is have a mechanism that moves 90 degrees, that's fine. If you need really angular, very fine resolution, say 1-degree control of your servo, that may not be good enough. Sorry that was fast at the end. I will post a better commented version of this code As usual, I will be here after lecture for questions, and I will try to swing by the lab this afternoon, okay? Thank you and have a good weekend.